Hello and welcome to this new video where we discuss various papers in physics and mathematics, which have been published, recently and less recently as well. And the idea is to get some awareness of some ideas that basically go kind of against the mainstream and that are worth discussing sometimes like kind of very deeply and much more broadly. So today, the article we are going to look concern the entropy of a black hole. Now, before I actually move on, I just would like to highlight that some of you may know, and I've explained that in a particular video, that I'm not particularly convinced of the mathematical coherence um, and consistency of typical black hole models, especially the Schwarzschild model, and I've explained why. It's both a historical and mathematical inconsistency as far as I'm concerned. And that's it. So if you want to have a go, please kind of click on the link that I've put here. And otherwise, let's move on. So if we admit, though, that there is such a thing as a Schwarzschild black hole, for example, then there is a corresponding black hole entropy that has been proposed by Bekenstein and Hawking. And that's what is being discussed in this paper. So this paper was published in the journal Entropy. That's actually a fairly reputable journal in the field of entropy and information theory. And the title is Black Hole Entropy, A Closer Look. Okay. Now, the idea is basically the following. So I'm not going to go into much details, but the point is that if you consider an entropy expression, so that would be stemming from information theory, that could be stemming from statistical mechanics, statistical physics, from von Neumann for the quantum version of it, etc., then often there is the axiom of additivity. So when I say axiom, is that this is one of the properties that an entropy function should have. That's additivity. Now, one of them is so-called Boltzmann-Gibbs, and that's what here is kind of summarized in equation 1 to 4. And if you use this particular entropy, you end up with the Bekenstein-Hawking formula that the entropy is proportional to the area of the horizon of the black hole. Okay. Now the problem with this is that this is inconsistent with thermodynamics, and the author of that paper is in particular very much interested in thermodynamics. He's an expert in thermodynamics, and he does take issue with the fact that that's not consistent with thermodynamics. Now, when you have a gravitational system, one of the consequences of it is that you do have automatically a sort of breakdown of one of the assumptions of thermodynamics, for example, that the internal energy is extensive. Okay, and one of the reasons for that is because the gravitational interaction is so-called long-ranged in such a way that basically if you take very, very far away kind of objects, then the energy is not going to be just the sum of the energy, but however far they are, there is going to be an influence between the two parts, which is not the case if you've got a sort of short-range interaction. Okay. Now the consequence of that is that the energy in that case is not extensive, and you need to kind of regularize the energy to make it extensive. Okay, so that's one of the issues, but that's not surprising. Okay, that's an issue, but not surprising. However, another quantity which is supposed to be extensive is the entropy S, and that's supposed to play a very important role for the entirety of the rest of the formalism of thermodynamics, okay, the extensivity of the entropy. And so the author and many others actually do take issue with this proportionality to the area instead of the volume, if there is such a thing as a volume, but let's say the right dimensional scale of the entropy. So what they suggest here is, and that's actually written here, is they suggest to, when we have an additive expression for the entropy, that is thermodynamically non-extensive, then essentially we should save the extensivity property at the expense of additivity instead of the other way around. And that's what they contend. That's a philosophical and conceptual premise, and people need not agree with this, but that's kind of the premise that is taken here. And so, as it turns out, Thales has developed non-additive entropy, and in fact has been quite successful in showing that they can be very useful in many, many situations, for long-range interaction, for example. So, um, so what do they do in the end? Well, one of the things here is that they highlight as well why is it that they want really to maintain extensivity. And the first is that that's the first here argument is that there is a lack of physical necessity of violating the Legendre structure of thermodynamics. So the formalism of thermodynamics is tightly knit together via a so-called Legendre structure. So you can go from one particular so-called Massieu potential to another via a Legendre transformation, and this gives rise to a plethora of equations and relationships between different thermodynamic observables. For example, the so-called Gibbs-Duhem equation, which relates the pressure, temperature, and chemical potential, is essential to basically stating that they are so-called equations of state in thermodynamics, and they come from both the Legendre structure of the theory and also the extensivity of some of the Massieu potentials, including the entropy. Okay, so that's the first aspect. So essentially, if the entropy is not extensive and the Legendre structure of thermodynamics is not kind of satisfied, then, like, in a sense, thermodynamics kind of explodes, okay, and it needs to be rethought completely anew. I'm not saying it shouldn't be done. I'm just saying that that's not what people do when they use the Bekenstein Hawking formula. They just use a formula and they kind of forget about thermodynamics, it seems. And then the last part has to do with, or the second argument has to do with a somewhat recent argument, let's say from the last 20 years or so, which is to use a mathematical formalism called large deviation theory, which can be used to justify the extensive character of usually actually any kind of so-called Liouville functionals, and here in this particular case, the entropy as being extensive. Okay, um, and basically both these points tend to be going hand in hand. They seem to be coming from independent kind of sides, if you will, but then they actually match very well together and are consistent with each other. Okay, so for this reason, this particular author does want to commit to an extensive entropy, and cutting directly to the result, they suggest, so this is a Bekenstein-Hawking entropy, and they simply suggest that the new entropy should be proportional to the Bekenstein-Hawking entropy, but then to the power 3 half. Now, this is, as far as I'm concerned, this looks like a quite minor correction, and I think a fairly it's insofar as it reads, it seems to be perfectly okay. It's going to change plenty of things, right? Because there are plenty of papers that have come out on the entropy of black holes, on the thermodynamics of black holes. So actually adopting a different expression, even if it's a simple change like that, is going to change many things with regards to many conclusions and results drawn on the thermodynamics of black hole, perhaps even on the thermodynamics of gravitating kind of systems like stars and stuff. So, I will leave you here. The whole point is that is to be aware that there are discussions going on that are basically theoretically kind of valid, basically where people want to say, yeah, these equations do make sense, but I think we need to uphold some aspects of thermodynamics which are currently violated by this equation that has been used now for like 40 years or so. So that's it. If you've got any comments or questions, please do ask them or post them in the comment section. And otherwise, see you in the next video.